All right, good evening. Let's start. I have written a lot of things on the blackboard because I want to summarize what we have seen recently. So remember, the system we are looking at is something like this. It's a discrete time system. So n is a time. And the evolution of the system is, so x represents a random variable. It's a xn is a vector in R capital N. And we will see later on some example where capital N is huge. But so it's a random variable. We have the evolution given by f of xn is, x at time n plus 1 is a function of x at time n, probably also explicit dependence on n, plus a model error, which follows a certain distribution. And at one point, I need its covariance, which I call Qn. We also have an observation. The observation is usually a function of the system. And I gave some example in the past. So H is an operator or matrix. It depends if it is linear or not, which take xn. It can be also depending on n, and gives you another vector. Yn is typically in Rn, in Rm, and m can be equal or smaller to n. And we also have an observation error, which has a certain covariance. Now, for studying this, we have seen already several algorithms. The Kalman filter is a simplest one, but you have to assume many things. You have to assume that f and h are linear. You have to assume that your system has a Gaussian distribution. Your initial distribution is also Gaussian. So you have many assumptions for this. But nevertheless, once you have this assumption, it's a closed system, so you can really write everything. Then we have seen this extended Kalman filter. You don't need to assume that the evolution f is linear. You don't need to assume that this operator h is linear. But at every time step, you do a linearization. So it's a simplification. When you have very chaotic system, of course, it's not good, but nevertheless, it gives you a first approximation. Then the two other approaches, which is this one, stochastic ENKF on the one here, they use a different idea. You are going to have J simulations of your system. So you take a focused ensemble. So it's a family of, okay, here I have already evaluated, but it's a family of evolution of your system for focused, and you take this J from 1 up to J. This is typically a number between 10 and 100, so it's not a very big number. Kiwen has shown an application 1 or 2 weeks ago, and she only took 3, or for another application, 15. So it's really a small number compared to capital N or capital M. And whenever we have one observation, we are going to update our focus and by taking this observation into account. And we have a new family of analysis ensemble, so a family of system after the observation. So the F is for focused, A is for analysis. So we have seen this. And ENKF tells you it's an algorithm how to, starting from a family like this, how to get, after the observation, a family like this. And it's stochastic because at each time point, you have only one observation, but it makes your system unstable. So what you do, you create some fake observation by, you have your real observation, but you add some noise. And I take it centered at 0. So you have a family of, let's say, Gaussian process, but it doesn't matter. A family of random noise. If you subtract the mean value, then the expectation of this family is still this value, precisely because you subtract the mean value. And when you write the algorithm, I also introduce this Gothic X and Gothic H, which is simply here, this vector, which is this focus xj minus the mean value over this family. And you divide by this. And you also need this where you have H. So, no, sorry, it's F. No, it's H. This is correct. You have the observation applied to this. It might depend on N explicitly, minus the average value of this observation. And it plays a role when we have defined the algorithm, and I need them later again. And for simplicity, at one point, I will not write this NF all the time, so I forget it. So what is this? It's just a collection. These are vectors. This is a vector. This is a vector in Rn. This is a vector in Rm. But if you put, you can create a matrix by putting J elements next to each other. So you create a matrix which is N times J, or a matrix which is M by J, just by considering this family. So for the computation, it's convenient to consider this as a matrix. And there is an algorithm which I haven't written, but starting with a family of ensemble forecast, taking one observation, you create this family of analysis, and then you iterate by using this equation, you get the next forecast. And last week, I also introduced this deterministic ENKF, which is called also ensemble transform Kalman filter. You don't want to have a stochastic process, so you want to avoid this, so it's a different construction. What is at the root of this construction? Whenever you have a family of forecast minus the mean, you get the covariance. This is the covariance of a sample just by this formula. You divide by J minus 1, and you take this time its transpose. And it gives you the expectation, or you take the expectation and it gives you the covariance of this sample. So we would like to do the same for the analysis. So once you have taken the observation into account. So we would like to have this, but we don't know yet how to define this Gothic X for the analysis. So I gave some formulas last week, and it was a rather long derivation. First, we compute the mean value. So the mean value over this analysis ensemble is given by a certain formula. You have the forecast mean value, and then a product of some matrices. Here you have the observation, and as you can see, I don't create any fake observation by adding a random noise. I have only one observation at time n, minus this operator applied to this mean value. There is a t, and it's going to be defined. X is defined there. This h is defined here. So this is a mean value. But then you create a family. So always think of like this. Okay, I do a picture in R2. You have one point or one vector, which is a mean value. And then you would like to create a certain number of observation or a certain number of vectors so that you get this as a mean value. So first I give you the mean value, and then I need to define these different points. And it's another formula. So you take the mean value plus this, you take the J column of this matrix. And this was the end of the last lecture. And I said U is any orthogonal matrix, but it has to satisfy one more condition. Be careful, this is not the unit. I mean, it's a vector 1, 1, 1, 1, 1. The condition is that U applied to 1, 1, 1, 1, 1 has to be 1 also. And T was defined like this. And so we have to check one more thing, but once you have this family, this ensemble of analysis, so the analysis ensemble, and you can go to the next step. So you focus the next value by taking F on this vector, depending on N plus a model error. However, what was the missing point last time? If I take the mean value and add something, I have to be sure. So I started with this mean value and I have added something and got these different points. I need to be sure that the mean value of this is really this. So this is where I want to start. Do you have any question or remark? I know it's a long story that is hidden here, but I'm trying to recall where we are. And by the way, yes, on NUCT, you are now asked to fill some questionnaire, evaluation questionnaire. It's like this at the end of each semester. Please take enough time and fill them. It's maybe not so important for you, but it's important for us, the administration, use these questionnaires. So please, before the end of the semester, you have a few, maybe 2 or 3 weeks, just fill this questionnaire, probably for all your courses. So what I need to do now, I need to finish the argument. So we have to check, and it's a nice argument. Have to check that if we take now the sum 1 over j times this x naj, I do the sum 1 up to j, which I have defined like this. If it is well defined, it should give us this value. Usually you define this mean value by this formula, but in this argument, we start by this mean value. So I need to check this. But please observe that this is equivalent to the sum j from 1 up to j of this Gotic x t1/2 u index j is 0. Because if it is 0, then it means when you do the sum, you are just summing j times this and you divide by j. And I'm still going to write this slightly differently. This is equivalent to this x t1/2 u. The vector 1, which I have introduced, is 0. Check. When you apply a matrix to 1, 1, 1, 1, 1, it gives you the first. Is it correct? Yes, yes, it is correct. You can check. When you apply this vector, this matrix to 1, 1, 1, 1, 1, it has to give you 0 all the time. Okay, so I need to check this, but now I have an assumption on u. So with this assumption, it's the same as x t1/2 1 is 0. Right? I'm using here the assumption. Now, the first time I saw this, I doubt that I could prove it because t is this one, and you have t to the power 1/2. So I was wondering how you can prove it. But still, it's true. So let's check it. So this is what we have to show, but observe that what is this matrix applied to 1? Can you guess what it is? The definition is no more here, but this matrix is made of xj minus the mean value at so you do the collection first. This is x1 minus its mean value gives you the first column, then x2 minus the mean value. So when you apply to 1, 1, 1, 1, 1, so when you take this matrix and apply it to 1, 1, 1, 1, 1, what you get the sum j1 up to j of xj minus the mean value. This gives you 0. So this is true. You have 0 here. All right. So if I know this, I just have to show that this T1/2 applied to 1, give me 1 again, because then that's okay. So it implies we have to show that T1/2 on 1, this vector 1 is 1 again. But this is equivalent to the value 1 is an eigenvalue of T1/2 with eigenvector is 1, right? This is just equivalent. This equation means it's an eigenvector problem. You can just add the value 1, and you have this matrix applied to 1 is 1 times 1, the vector 1. So this is what I need to show. Now, T1/2 is a symmetric matrix. This should remind you something from linear algebra. You can diagonalize it, right? And if you diagonalize it, you put the eigenvalues on the diagonal, and one of them is 1, right? So it means T1/2 can be diagonalized with 1 somewhere on the diagonal. Because on the diagonal, you have all the eigenvalues, and you know that 1 is at least one of them, right? Now, when you have a diagonal matrix, do you know the eigenvalues of any power or any function of a diagonal matrix? You just take the function applied to the diagonal matrix. This is something you should have seen. So it means 1 is also an eigenvalue of, I'm going to take T-1. I take a function of T, because I'm thinking I go to this diagonal matrix, then I take a function of it. Let's take let's take this matrix just for a second. When you take the square of this matrix, the two eigenvalues are going to be 1 and 4. The good point is 1 stays the same. So when you take T⁻⁻1 instead of T1/2, 1 is still an eigenvalue, because it's this, I'm taking a square and then a power -1, keep 1 at the same place. So 1 is still the eigenvalue of T-1, and you keep the same eigenvector with eigenvector 1. This is something from linear algebra, and in fact, it's even here you have an equivalence. Okay, so what is T⁻⁻1? This is what I want to show. I mean, I still want to show that this is an eigenvalue. 1 is an eigenvalue. We don't know it yet. But T-1 is easy. T-1, if you look at the definition, it is 1. Oh, sorry, this is really the matrix 1 J times J plus H transpose a certain matrix -1 H. This is the definition of T-1. So you have to show this. This applied to 1 is equal to 1. Now, can you see that this is true? In fact, I should put a question mark, because we haven't proved it yet. This is what we want to prove. Can you see why it's true? Observe. look at the definition of this curly H, or this Gothic H. H on 1 is equal to 0 for the same argument as here. It's also a sum of one vector minus the mean value. So when you apply it to 1, it's also 0. So you get that this term applied to 1 is 0, and you get this identity matrix applied to 1, 1, 1, 1, 1 is indeed 1, 1, 1, 1, 1. Okay. Then we have identity matrix J times J applied to 1, which is really equal to 1 times this vector. So we played with equivalences whenever it's necessary, and so we get the result. Okay, from here, everything was made of equivalences. So we have obtained this. So if we summarize, we have shown this relation. It was not granted from the beginning, but we prove it. Okay. So I think it was a nice argument, and you really need to use linear algebra. Remember what is a diagonal matrix. Take a function of this diagonal matrix and you get it. Okay, now we can move to the next section. I was expecting that it would be a simple section. It's not so simple. This is called inflation. Localization. I have to explain. So far, space has not really played any role. And I will be more explicit in a second. But think about weather forecast. In a problem with weather forecast, it's a continuous problem, but you discretize. So whenever you do a discretization, usually you take a certain surface, you discretize it like this. And so you're going to have plenty of points. We call this point PL. This is small p. So it means, so in application, what I called X at time L takes a component L. This is a component L. Is or represent a certain quantity. Like the temperature or the direction of the wind or whatever, a certain quantity at point T. So one entry of this very long vector is in fact a certain quantity at a point PL and at time N. Then for discretization, I have written more details in the lecture notes, but I try to explain here. For the discretization of a continuous model, so what people deal usually is almost with 1 million or 10 power 6, 10 power 7 up to 10 power 10 power 10 points. So it means a capital N is really a huge number. So then for discretization of a continuous model, one gets 10 power 6 up to 10 power 10 points. Pn, namely a set E, a set PL L is equal to 1 up to capital N, included in RD. And D is usually D is equal to 2 or 3, depending if you deal with a problem in 2 dimensions or in 3 dimensions. So it means here L is typically 10 power 6 to 10 power 10, such a big number. Now, what is the relation with capital N we started with? At every point, you might measure the temperature, the pressure, the direction of wind. So you might have more than one information. So if N information, N information are collected at every L, we have now capital N is capital L times N. So this is a relation between the number of information you have at every point and the number of points. So yeah, N is really huge. However, as I already mentioned, J, one usually take J simulations is J of order 1 to 100. It depends, but I mean, these are small numbers. So you want to represent something which contains many, many variables, but you want to represent only a small number of such models. So you have plenty of problems, and I'm going to mention 2 of them. One is what you can solve with inflation, and the other one is what you can solve with localization. So the question is, can one really represent covariance of the physical system is only J simulations? How you should think about this notion of covariance? This covariance is always it's also called the spread. You have a mean value X bar, and you have a few points around so that it gives a mean value. But the question is, if you have only J simulation, be careful. This is not a representation in space. These are vectors, which are precisely vectors in R capital N. But with very few points, can you really represent all possibilities of your system? So the spread is related to this set of points around the mean value. And the first problem we face is the following one. Often the spread is too small. So what means the spread is too small? And this is measured with the covariance. What means the spread is too small? Let me make 2 pictures and you will easily see. If the mean value is the same, a small spread means all the values are very close to the mean value. This is a small spread. All your vectors are all very similar. And this is never good because it makes your system unstable. So this is a small spread. Which means small covariance matrix. And remember, 1 week or 2 weeks ago, precisely for dealing with this, we had added this stochastic noise. And we can do something similar here. So I want to avoid, or I want to do something if, when I use any algorithm, it turns out that the spread is too small. And in this case, I need to add, people speak about filter divergence. About filter divergence, this is a word used. The spread is too small. Because I have added one and cannot assimilate the observation. What do I mean by this? In all this business, whenever you have an observation, you have one observation, this is a y. It should be inside the spread. If your y is here, you can already get that your system or your focus is not good because the observation is not even close to any point from the focus. So this is what you want to avoid. So there are two techniques for dealing with this. It's a little bit artificial, but it works. So the first approach, so two methods for dealing with this. And you can apply these two methods to all the algorithm I have mentioned before. So the first one is called multiplicative inflation. And it's quite easy to make a picture of what we are going to do. Take this picture and simply inflate these points or the distance by a certain factor, and you end up with points here. And if you do it properly, you're going to keep the same mean, but the spread or the covariance is going to be bigger. And this is quite simple. So what you do with this multiplicative inflation, so right after the focus, when you get this family X and F, J, you replace one of them, or any of them, by this X and F plus a coefficient rho times X and J. for row bigger than 1. So look, you replace one point, take one point and you replace it by this expression, it's exactly going to give you this point. And now if you take the mean value of this, so you do this for every point. Maybe I should give a name. I call this XNF tilde. J, sorry, there is a J also. And then the mean value, so XNF tilde mean value, so that you get by taking 1 over J, the sum of these values, or these vectors, is the same. It's XNF. So you keep the same value, but the covariance matrix is multiplied. Multiplied by this coefficient square. You can check just by taking the definition of the covariant matrix. I gave it before. You get this coefficient rho square, and precisely it is this picture. From something which was too concentrated around the mean value, you get something larger with the same mean value, but they are more spread, and so that you can manage to have your observation inside. It's artificial, but it works. And so this is just a multiplicative inflation. Another option so what is called the additive inflation. Let me do the picture again. We had this mean value on points which are too close to it. I'm going to add some random noise of mean value 0. And if I take this random noise big enough, so I'm going to transform this into this one, this here, this one maybe here, this one here, and this one here. If I do it correctly, maybe my picture is not very good, but I can manage to keep the same mean value. So let's look at this. It's correspond to adding a larger model error. If you look at the very beginning, I have introduced this psi n as a model error. So again, after the focus step. Again, it means we define x, again, nfj tilde. I take this x nfj plus, I take it like this. So what does it mean? You take psi follow a certain distribution, psi n follow a certain distribution. So you take j vectors, these are vectors in Rn. So you take j vectors according to this distribution, you compute the mean value, and you add to each of them one of these random vector minus the mean value. And it implies again that if you do the sum, oh, I can write do the sum x n f tilde mean value is the same mean value as before. But what has changed here? But T&F tilde has increased. I think I have introduced at the beginning this Q n. This is a covariance matrix of the random process. Psi n. So in this way, you increase again the spread or this covariance. And in fact, you can, if you look at it, these are independent processes. So you can do both simultaneously according to what you want. You can add this inflation, and you can also add a sufficiently large model error. So both can be applied simultaneously. Both can be applied simultaneously or separately or simultaneously. Or simultaneously. This is one option that you can, you have two options when you observe that the algorithm has a filter divergence. So when the spread is becoming too small, and this happens because it's an iterative scheme. So sometimes the covariance is just becoming too small. So you just inflate it at every step. And I think in the application that Kiwen is going to show us either next week or next week, she used the inflation precisely of rho is equal to 1.06. So you don't need a lot, but something slightly bigger than 1. You know, when you do simulations, you can even check how this covariance decay or increase, and you can control it or keep it constant or do anything. Right, so this is the first problem, divergence, filter divergence. Now, the other problem, let me just come back to this picture. When you discretize, the problem is, can be the following. You have in this long vector, remember xn is a very long vector, you have something related to this point and something related to a point here. In the Kalman filter Kn, and I'm going to recall, when you define this, it contains all information. So it means it contains this information and this information. And in a sense, they are not at a given time n, these two things are not related. There is only a weak correlation between these two things. Of course, if you let time evolve, then some information can go from one point to another one. But at a given point n, these two things are usually not so much related. On the other hand, Kn takes everything into account. So it's a little bit artificial that you construct something with information which are not related. So we want to make what is called localization. So I want to keep the information here around this point and keep the information around this point, but not mix them too much. So this is this idea of localization. So this is the second, I had a first when I spoke about inflation. The second problem is localization. So far, the Kalman, what was called the Kalman gain matrix, is a global object. It's constructed with everything. But this creates some correlations between points which are far apart. When we do a discretization, of course, it's not for all models that you have this problem, but precisely when you do the discretization of a large system, discretization. So you would like to avoid the creation of these correlations between points which are far apart. Again, there are two techniques. But I need to be a little bit more precise about this picture. By the way, if you have any question or remark, you can interrupt me at any time, of course. But yeah, I want to deal with this situation. We do a discretization of a large system. Points can be far apart. Kn contains everything, and I want to localize. So the first is called the covariance localization. But for doing this, dealing with this, I need to be more precise about the notation. We have index X, N, L, or no, we have to index the components. And more precisely. What I mean by this precisely, I need to give an index which is meaningful. So we have a point P, we have a point P prime. I want to reflect this in the index. And I haven't done it so far because I have never treated such systems. It was inside, it was taken into account, but now I need to be more precise about this idea. So how I need to index this? So let PL, it's a small p, included in RD, a family of points like this. So denote now I want to say that these are coordinate points. It's a grid in RD. And let I belonging to a finite set index or index information or index n information each point. So at every point you have probably more than one measure or one information. I consider that you have n. I consider this number constant. You could make it depending on L, but this is not really interesting. Be careful, this N has nothing to do with time, but because I already mentioned this, we have capital N is capital N times small n. This is why I introduced small n. And then first consider, now I'm going to consider this vector in Rn. I will consider as xn, and the index is pi. So what do I mean? P is 1 point on this lattice, and I is 1 up to n. So every entry, every component of this huge vector is indexed by 1 point and 1 index. 1, for example, for the temperature, 2 for humidity, and so on. Right? So this is a new indexation of this vector in Rn. So, okay, with P. Yeah, if I want to be precise, but I will forget this L in a second. L is between 1 and capital N, L, and I is between 1 and small n. But and this small n here, sorry, is a time. But from now, fix L and call it. I don't want to keep this index L, it's not really necessary. So I will just call it P. So it's just a change of name, but now these new names mean something on a grid. So you really have points on a grid. So with this notation, I just want to rewrite a few formula. Let me remind you, we had P and F. So the covariance matrix for a sample, it's given by 1 over j minus 1. And we had this sum over j from 1 up to j. So this is the definition of the covariance of a sample, but just be careful. These are vectors in R capital N. Even for J is just an index for this family. So now with this new notation, what I should write? This was before. This was before one had this. Now becomes PNF. So observe, this is a matrix. Maybe I should mention this is a matrix M n times n. You have a vertical vector of dimension n times 1, a horizontal vector 1 times n. You get a matrix. Or you get n matrices, or j matrices, but you sum over j, 1 up to j. So this n by n matrix, now I should write it like this. I T prime I prime. So now the index is a pair P and I. So this is Pi and Pi prime. I want Pi prime. And now this is given. So this is an entry of the matrix. It is 1 over j minus 1, sum over j, 1 up to n. And then we have this vector x n f minus x bar entry Pi x n f minus its mean value. And oh no, sorry, I have to put j here, T prime I prime. Yes. So now the index, which was an element of from 1 up to capital N, is a pair Pi and Pi prime. So just be careful about this. It's the same object, but the indexation is slightly different. But the point is precisely, I don't want to keep this correlation matrix like this, because if P and P prime are far away from each other, now it's meaningful. If P is here and P prime is here, I don't want to have a big correlation between them. So I want to do something to reduce the correlation in this between, and in the formula between P and P prime. So I'm going to introduce the correlation matrix. I'm going to call it rho. It's an n by n matrix. It's not just a coefficient, but now it's a matrix. And again, rho index Pi, P prime, I prime. This is the way I index one entry of the matrix. Is going to be, so this is one entry of the matrix. I want to have something like a certain function which depends only on the distance P minus P prime. I want to introduce a function which gives me an information about the distance between P and P prime. And I can have a dependence on I and I prime. I will explain why in a second. So with this Cii prime, it's a function from R plus to 0, 1. Can you tell me if it is decreasing or increasing? What do you think? Okay, I haven't introduced so much information, but I want to call it a correlation matrix. So it should decay. If 2 points are far away from each other, the coefficient linking these 2 points should be small. On the other hand, if 2 points are close to each other, I want to say, oh, they have a correlation. So I want to define a function which looks like this. Why is it defined on R plus? Because I just take the Euclidean distance or the real distance between these 2 points, and I want something like this, going to 0 quite fast. This is Ci as a function of R plus. if the distance between 2 points is big, they should not be related. Now, why is it depending on I prime? This, I mean, I take it general, but again, if you think that the first component I is the temperature, the second one, the humidity or so whatsoever, maybe the decay with the distance can be different for the temperature or humidity or anything. So you have this freedom to keep a dependence on what you measure by keeping this function I prime depending on I prime. Or if you want to say, oh, it doesn't matter what is the information you measure here and what is the information you measure here. You just want to have a function which depends on the distance. Then you take the same function without this dependence on I prime. This is up to you. But for free, I can do it like this. So I define this matrix. And now you can guess. I'm going to do a kind of product between this information and this matrix. But I need to define this product. But with this, I'm going to concentrate all information around this point will be related to this point, and everything related to P prime will be centered around P prime. And now there is one exercise. So I have defined this matrix like this. We also impose that this matrix row is positive semi-definite. And usually we write it like this. So what does it mean? It means that whenever you'd consider a row applied to a vector x and take the scalar product or multiply it, so this is a vector, and you take the transpose vector, this is the same as the scalar product between x and row x. We want this to be smaller or equal to 0 for any x in R capital N. This is a notion of positive semi-definite. Now, in a sense, I believe that it follows from this definition, but I'm not fully sure. But it's easy to impose it in addition. And the question is, does it follow from this definition? Probably, but I couldn't prove it quickly. All right, so I have now these two pieces of information. This covariance matrix and this matrix, which I call the correlation matrix, localizing the information. Then we set P. Maybe I should put a small bar here just to make a difference. This matrix PNF, and I will now add a letter L for localization. I define it as this row P. Do you know what is? It's not a product of two matrices. This is called the Hadamard product. Do you know what it is? Who knows what is a Hadamard product? It's called a pointwise product. So let me define. When you have two matrices, usually you have a certain way to compute the product of two matrices, but you can also simply do the product pointwise. This is called Hadamard product. So what is this Hadamard product? A B entry ij is simply aij bij. You really just take the two corresponding entry and you multiply them. Okay. This is called Hadamard product or pointwise product. It's quite clear why you call it pointwise product. Of course, if you do the product of two matrices, you shouldn't do this, but it's another product. What is a good feature of this product satisfies what is called the Schur lemma. If A is bigger or equal to 0 in the sense I have introduced before, and B is also bigger or equal to 0, then A Hadamard product with B is bigger or equal to 0, which is good. Why is it good? The covariance matrix, you can check the covariance matrix had this property, almost by definition of the covariance matrix. Now, maybe the covariance matrix was B. Now I have constructed this correlation matrix and I impose, or it follows from the definition, that it has also this property. So it means that our new correlation matrix L is also bigger or equal to 0, which is what you expect for a correlation matrix, which is expected for a correlation matrix. And if you think about it, I have done exactly what I wanted with this construction. We had this grid, and I have I kept the correlation matrix locally, but if this really decay to 0 quickly, I don't have any more correlation between this region and this region. On the other hand, I should not make a decay too quick, because still, sometimes you have some correlation between some regions. So it's also part of the game to find the good function here, not decaying too fast, but also not too slowly. So it depends on the problem or on what you do. But yeah, with this product, you have created a new covariance matrix, which is more local. And now you can insert this in all the algorithm with the Kalman gain matrix. So now, if H is linear, so this, remember this H is the observation operator. And quite often it is linear observation operator. It gives you only a few information from a bigger set. So if H is linear, then the Kalman matrix we write it, we can replace NF by this P NF localized. And this, if you look back at some formula with the Kalman matrix, you now get this rho P F H transpose, and then you have H rho and F H transpose plus Rn minus 1. This is some of the formula we have seen for the Kalman matrix, either in the initial Kalman filter or in EKF. We have seen this. You have these kind of matrices. It is assumed that either H is linear or you take the linearization. But we have replaced this covariant matrix by this local version. Now, this is not what you see often in the literature. What people write is of this type, and I will show you how you get it. You often see this. Which is simpler from the computational point of view. And you can wonder, oh, how can we get this? It took me a while. It's not trivial. You have, because look, this is the pointwise product, as I mentioned, or let's look here. You have a pointwise product, but then you have a product of 3 matrices. How can you extract this pointwise product? If you don't assume something, it doesn't work. You can try, write a product of 3 matrices, write with this, you have 2 sums, you cannot extract this. So how do we get this? We need one more assumption. And it's a nice computation. So it's, you know, it's always nice when you understand what people are doing. So let me explain what is the additional assumption with locality, local assumption. Let me explain. If we assume H is local, what do I mean by this? Remember, H, I'm still in the case when H is linear. H is from Rn to Rm. What do I mean by, so it, Rn is everything. But what I mean by local, I mean it's going to take a local information and send it to something around this point again. It's not going to mix everything. So let me be more precise. So if H is local, we can go one more step. So if H is local, I will give a definition. And if Ci I prime does not depend on I on I prime, so it's if it only depends on this distance, we have. So the first H is a big matrix. So I look at its entry Pi, Pi prime. If it is local, it means that this is a H, P, I prime, Honecker P, P prime. Look, it's a matrix. The points are indexed by P, P prime. If I want it to be local, this matrix should be diagonal. Otherwise, it means it mixes the information at 2 points. So it means we have a Honecker delta. It means this is 1 if P is equal to P prime. It's not 1 otherwise. And this is now a number which depends only on P, I, and I prime. This is the notion of locality. So now we can do the product of two matrices. So this is Kronecker delta. Then, so let me compute this part first. Then this Adama product PNF HT. So this is a big matrix. So I need to evaluate it at PI, P prime, I prime. Now, we have one matrix here, we have a second matrix here. So it's a product of two matrices. So you need a sum over Q and J. Q is replacing P. J is the index for the second entry of rho P. I should write rho of the distance P. No, let's keep rho PQ, but rho PQ. The entry of this matrix, because this is rho, C, this is C of P minus Q. I just write it in a shorter notation. This is C of P minus Q. It depends only on PQ and not on I on I prime. This is my assumption. Times PNF entry PI QJ. Yes. H P prime I delta P prime Q. Okay, you can check I have taken the two assumptions into account. And also the fact that we have a transpose. This is why I first put P prime I prime and I and P prime and Q. Now, you can do this sum over Q because you have this Kronecker delta. So it makes, I just factor this rho P prime because of the Kronecker delta, and you still have a sum over J of this P and F. Then we have PI P prime J times this H P prime I prime J. Oh, sorry, there is a mistake certainly here. This is a J. And now, if you look carefully, this is nothing but rho of P N P N F H transpose, everything evaluated at Pi P prime I prime. So you can check this computation at home. It's not difficult. You just need to write the definition of a product of two matrices. Use that this one has a Kronecker delta. Use that this rho does not depend on I prime, so you can factor it outside, and then you get this. So you can get it. And the same, if you do the same computation here with the same assumption, you can check that this factor can be put here, and you end up with this formula. So you need really these assumptions in order to do it. All right, this is a formula that you can find in the literature when people are calling about covariance localization. You replace the initial formula in the Kalman filter by a formula with these two covariance matrix. And then the rest of the algorithm is the same. So this is fine for these two algorithms here, Kalman filter or ensemble Kalman filter. It doesn't work all the time. So if remark, two remarks, if H is not linear, because I have used it, we can replace, we can use its linearization, which is what we do in ensemble or extended Kalman filter, the EKF. And this is the first point. But the second point, if P and F does not appear in the formula for Kn, we need another approach. And this is what I'm going to do. And for example, if you look at what we have done at the beginning for what I called ENK, or the deterministic ENKF, what I recall at the beginning, this does not appear. It was not introduced. So it means I cannot do this. So this approach works if you really have the covariant matrix and you do something with it. But in the approach I have introduced before with T1/2, we don't use this covariant matrix. So you cannot do it. And there is another popular approach. Let me just start with it. So, and this is called the second R localization. This is the second approach in R localization. It consists, let me write the sentence. Reducing idea is slightly different. Before, in the first approach with covariance localization, we are really destroying, in our computation, we destroy the correlation between these 2 points. Right? Now, we want to do something else. In the Kalman filter and in the process, and especially here, we have also observations. So an observation is maybe taking place here. But this observation should have no influence here at time n. So I want to destroy in the formula for the Kalman filter the influence of this observation on points which are far away. So how to do it? We shall rescale scale the R matrix, but I have to explain what it means. I need to recall some formulas for this. And it will become clear. Recall that this, that I have introduced before, this xn code for deterministic ENKF. And by the way, this deterministic ENKF is also called ETKF. So what I have introduced at the beginning, we had this is equal to this. No, it was analysis. The analysis after the observation is equal to x bar n a plus this square root of j minus 1. This x t1/2 u entry j. I just recall the formula which were already on the blackboard before. And T is given by this 1 plus H transpose Rn minus 1H. This is what we had earlier. Just for information, I have not written again. This should be with a NF, and the same for H, it is H and F. I have not written it. So if we want to reduce the impact on this observation on points which are far away, the way we are going to do it is playing with this R. And this is why it's called R localization. But of course, if I change this, I must be coherent. So I also need to change this one. I have no time to explain now, but remember, these are big vectors, and in fact, they depend on points P on a grid. So if you can make this depending on this grid, and such that if one observation is far away from one component here, that this observation doesn't play such a big role, then you have precisely done what is written here. You reduce the influence on one observation on a point which is far away from it. So next time I will just explain how we need to modify this in a coherent way to reduce these correlations or these things which are far away from each other. All right. I know it's dense. I encourage you to read your notes again or to read my notes again before the next lecture. So at most, we are going to have 2 more lectures, and at least half of one will be filled with one example about how to use Kalman filter or such techniques for controlling a chaotic system. You have a chaotic system, you want to avoid extreme events, so you can use these techniques. You focus something, you see, oh, there will be an extreme event, so you modify slightly your system in order to avoid an extreme event. All right. What you should remember, we have really big vectors. We have either some problem with inflation, so the spread is too small, we use inflation, or you have correlations which are not necessary, or even not expected. So you do something with localization. Okay. Do you have any question or remark?